In section 4.4 we look at another very important part of algebra, which is slope, and then similar to slope, rate of change. So slope is going to be defined as the ratio of vertical change to horizontal change between any 2 points in a non-vertical line. So this won't apply to vertical lines, but for any non-vertical line. And we can call that vertical change the rise, so how far up or down we go between 2 points, and the horizontal change we can call the run, how far to the left or right we go between 2 points. So in words we could see this represented as slope equals rise over run. This is a very common thing to memorize, rise over run, rise over run. Or in a little more algebraic terms we could say change in y over the change in x, because the change in y will give us the vertical change and the change in x will give us the horizontal change. And in symbols we typically use m to represent slope, and this is equal to the change in y shown by y2 minus y1 over the change in x shown as x2 minus x1. This comes from having a point P1 that has coordinates x1, y1, and then point P2 will have coordinates x2, y2. So in other words, look at the change in the y coordinates, y2 minus y1, over the change in the x coordinates, x2 minus x1. In a picture, we could look at something like this. Here's a line. Notice that this line is not vertical. And we have 2 points already selected. And remember that you can use any 2 points on the graph, but we would like to use 2 points that are hopefully at the intersection of 2 grid lines, because those are easy to find the coordinates of. Pardon me, as opposed to a point like this where we really would have a tough time finding those coordinates. So as we go from point 1 to point 2, we have a rise over our run. And notice the direction here. So going from point 1 to point 2, we have a positive rise and a positive run, going up and to the right, and a positive divided by a positive is, of course, a positive. And so a positive slope is always going to go up and to the right. And if you started here and went down, which is certainly acceptable, that would give you a negative. Then you would have to go to the left, which is also a negative. And a negative divided by a negative is still a positive. And so it doesn't matter which one of these 2 points you call P1 and which you call P2. Your signs should still work out the same. We also want to look at rate of change, and you'll see some examples related to this. This is simply a comparison of change in one quantity to the change in another quantity, and it's basically the same thing as slope, corresponds to slope. So examples, number 1, find the slope of the line in the graph below. So we want to pick 2 points, hopefully where we can determine the coordinates accurately, such as this would be a good point to use. And here we're at 0, 4. And this looks like another good point right here, which is at 2, 1. So we have our formula, y2 minus y1 over x2 minus x1. And again, it doesn't matter which one of these we call point 1, which one we call point 2. Let's go ahead and take 4 minus 1 over, now because I picked this as my starting y value, I have to pick 0 as the starting x value. We can't do a mix and match here. Pick one or the other. So starting with 4 for y means start with 0 for x and subtract 2. So we get 4 minus 1 is 3. 0 minus 2 is negative 2. And remember that when you have a negative in a fraction, it can appear in the denominator, or you could put it in the numerator, or as is more common, you can put it in front of the fraction. And especially in the case of slope, this will be more common to see it in front of the fraction, because right away now we know that this line goes up and to the left, not to the right. In number 2, find the slope of the line that passes through the point. So here we have our coordinates, and again, it doesn't matter which one we call point 1, which one we call point 2. Let's try this. So our y2 minus y1 will be 10 minus 2. And x2 minus x1 will give us 8 minus 6. So we end up with 8 over 2, which simplifies to 4. Now what if we had switched these around? Let's switch P1 and P2. Then we would have 2 minus 10 in the numerator and 6 minus 8 in the denominator. And we would end up with negative 8 over negative 2, which is still a positive 4. So it doesn't matter which one you call point 1 or point 2. Okay, 5, 1, and negative 3, negative 3. Again, we want to find the slope that goes through these 2 points. Slope of the line that goes through those 2 points. So if we look at, I'm going to go ahead and take 1 minus negative 3. It's always kind of nice to subtract a negative because we know that's just like adding a positive. And then 5 minus negative 3 in our denominator. So 1 minus negative 3 is 4. 5 minus negative 3 is 8. And please simplify. So we end up with a slope of 1/2. Okay, number 4, we have negative 4, 3, and 2, 3. So I'm going to take 3 minus 3 in the numerator and 2 minus negative 4 in the denominator. 3 minus 3 is 0. 2 minus negative 4 is 6. But 0 divided by anything is simply 0. And if you think about what this graph looks like, we have the points negative 4, 3, so we'll kind of make a rough idea like that, and 2, 3. This is a horizontal line. And go back to the idea of slope, where you have rise over run. And for any 2 points on this line, there is no rise. So it doesn't even matter what we have down here for our run. There is no rise, so we have no slope, or slope equals 0. Number 5, 2, 6, and 2, negative 7. So I'm going to look at 6 minus negative 7 in the numerator, and then we have 2 minus 2 in the denominator. So here we have 13 over 0, which hopefully you recognize right away is a problem. We cannot divide by 0. This is not allowed. And that means we're going to call this undefined. Remember, we said at the beginning that this whole idea of slope works for non-vertical lines. But if you were to graph this, you would see that we actually have a vertical line. 2, 6, 2, negative 7. And so here, when you look at the idea of rise over run, pick any 2 points on this line, and we don't care what the rise is. We know that the run is going to be 0, not allowed, so we call this an undefined slope. So anytime you have a horizontal line that's 0 slope, a vertical line will give you undefined slope. And those are 2 good special cases to remember. Number 6, the table shows the charge to rent a certain tool at a local rental company, and it's based on the number of hours that the tool is rented. Find the rate of change with respect to time. So what we want to do here is look at the added cost. So it takes, going from step 1 to step 2, $20 more, $20 more, and compare that to the change in time that the tool is rented. So here we're renting 1 additional hour, 1 additional hour. So we have a consistency here of 20 over 1, 20 over 1. So this is $20, 1 extra hour. This also gives us $20 over 1 extra hour. And the fact that these ratios remain the same indicates to us that this is a straight line, by the way. And so the rate of change here is what we just calculated, $20 for 1 hour. So $20 per hour. And if you were to graph these points, 120, 240, 360, guess what? That line would have a slope of 20. Okay, let's look at the next one. The table below shows the fee for renting a car for 1 day based on the number of miles driven. At least it was supposed to show it. So here, if you drive 20 miles, you get charged $24. 40 miles, you get charged 26, and then 28, and if you drive 80 miles, you get charged $30. So this rental fee includes a daily fee plus a mileage charge. And we want to find the rate of change with respect to distance driven. In other words, how much are we paying for each extra mile that we drive? So here, the rental fee went up by $2. Went up by $2. Went up by $2. Compare that to the distance driven, which increased by 20, and again by 20, and again by 20. Now, it's not important that we're going up by the same amount each time. What is important is this ratio, 2 over 20 stays the same. 2 over 20, 2 over 20. So the rate of change is equal to, we're paying $2 to go 20 miles, and we would like to get a unit rate out of that. So in other words, how much are we paying per mile? And if you take 2 divided by 20, you'll get 1/10. So in other words, it's 10 cents per mile. Okay, number 8, using the graph below, sketch a graph that models the following situation. Carmen gets into her car and accelerates to a steady speed. That's during period A. During period B, she drives at a constant speed until she reaches a parking lot. And then when she gets to the parking lot in period C, she slows down and parks her car. During period D, she's shopping, which means her car is sitting still. It's not moving anywhere. Then she returns to her car and accelerates out of the parking lot in period E. And then during period F, she drives home. She's really lucky here. There's no traffic lights or stop signs or anything. Just drives at a constant speed all the way home. And then during period G, she arrives home, she slows down and parks the car. And so we want to draw a graph here to show that situation where over the course of time we're following her speed. So during period A, she accelerates. And if we have a straight segment here, that indicates that she's accelerating at a constant rate. You could draw more of a curve if you wanted. The main idea we want to get across here is that we're showing a slope to indicate the change in speed. If she's going accelerating very quickly, we would draw a steeper slope here. If she were accelerating slowly, we would draw a lower slope line. So in other words, a segment that rises less quickly. Then during period B, she drives at a constant speed. So there is no acceleration. There's no change in speed, so we have a slope of 0. Then during period C, she slows down until she has a speed of 0 because she's parked her car. Then during period D, her car is sitting in the parking lot, hopefully not moving anywhere, so that should have a speed of 0. Then leaving the parking lot, she accelerates, then drives a constant speed going home, and then finally decelerates until she parks her car and again has a speed of 0. Okay, so again, you might have some variations here in terms of how steep your line is, whether you made this straight or maybe a little bit curved. But we want to get the idea across that she's accelerating. Constant speed shows a slope of 0. Decelerating, definitely at speed equals 0 while she's shopping. And then, again, accelerating, constant speed, decelerating. Okay, so again, remember that this is going to be a very important concept that you get from algebra if you haven't run into this already before. So good luck with slope and rate of change.